All right, here we go with topic 9.9, cell potential under non-standard conditions. So we're continuing our look at electrochemical cells, and we will be able to explain how the concentration of our solutions in our two half cells affects the cell potential or voltage in order to explain why cell potential decreases over time. So the first thing we need to understand is what standard conditions are. When we look at our list of standard reduction potentials with those half reactions, all the reactions are run at 25 degrees Celsius, so basically room temperature, and each solution that they're placed in, each of the half cells with their aqueous solution is 1 molar, so that we have the same conditions for every single measurement that's made. So we're going to be looking at what happens when it's not 1 molar. Okay, now we're going to take a look at non-standard conditions and what that does to our galvanic cell. So we have a basic one set up on the right. It doesn't have all the pieces, but it has enough for us to track what's going on. So our oxidation and reduction are labeled. Oxidation's occurring at the zinc electrode on the left and reduction on the right at our copper electrode. We can label our cathode and our anode. We have our cathode where reduction is occurring, so red cat. We've got our anode where oxidation is occurring, so anox. So we can use that to help us. And then we've got our electron flow. Electrons always flow from anode to cathode, so our electrons are going from left to right through our wire. Now, if we changed these conditions at all, change what was happening, it's going to affect our cell potential. Remember, our cell potential is basically measured where that wire is. So if we increase the concentration of our ions at the cathode, that will increase our cell potential, increase that voltage. So why is that? Well, if we had more copper ions available, they can accept more electrons, and that pulls those electrons across the wire more and allows a higher voltage. So increasing our concentration at the cathode increases our cell potential. If we did the opposite of the concentration at the cathode, so less than 1 molar, then it's going to decrease that cell potential, right? So in general, more ions available to react or be reduced allows for a greater voltage. So we want more at the cathode, more cats, to get us a higher voltage. Now the opposite is true at the anode. As the anode reacts, we're getting a buildup of zinc ions, right? As those electrons leave the solid zinc, we're getting zinc breaking off and forming its ions. So if we had a higher concentration of zinc ion, then we would have too much charge on the anode side. So our salt bridge would have to work too hard, all of that. So more ions on the anode side creates too much charge in that half cell. So the oxidation is more difficult to take place. So if we want to increase the voltage, we would have to decrease the concentration at the anode. Okay, so to maximize this situation, to maximize our cell potential in this galvanic cell, we would increase the concentration of our copper ions and decrease the concentration of our zinc ions. Okay, so we'd have more than 1 molar at the cathode, less than 1 molar at the anode. Changing the mass of the metal, so changing the actual solid zinc or solid copper electrodes, will not have a significant effect on our voltage, so that we can eliminate that as an option. So we're only changing those 1 molar solutions because that's going to have an effect on the voltage across our cell. So let's take a look at how we would answer a question based on this information. So we have a galvanic cell shown. It generates a cell potential of 3.17 volts when operated. So we can see how it's set up. We can see that it has that 3.17 volts across the top salt bridge. We have our magnesium and silver electrodes, and they are both in 1 molar solution. So it's a standard, it's under standard conditions. It also gives us the half reactions and their standard reduction potentials. So a second galvanic cell is made from the same two metals, and the measured cell potential is positive 3.25. Which of the following could be the reason for the second cell having a greater cell potential? So we can see we're starting at 3.17. We build a second cell, it has a higher voltage. So we're changing something to increase that voltage. Let's take a look at our options here. So letter A says the mass of the silver electrode in the second cell is greater than the first. Well, like I said on the previous slide, changing the mass of the electrode is not going to change our voltage. So we can eliminate A as an answer. Letter B says the mass of the magnesium electrode is being changed. Again, the mass of the electrode has no effect, so we're going to eliminate that. So if we look at answers C and D, they both show this notation. So let's look at that. If we have a chemical in parentheses, in brackets like that, it's going to mean concentration or molarity of that chemical. So brackets around the magnesium 2 plus ion means the concentration or the molarity of the magnesium ion. So when we read letter C, it says the concentration of magnesium ion is greater than 1 molar. So we're increasing that concentration of magnesium. And silver is 1 molar, so we're keeping the silver the same in the second cell. So we're changing that concentration of one of the ions. Now there is this part that says resulting in Q is greater than 1 and Q equals 1 for the first cell. So that part Q we're not familiar with and honestly doesn't change our answer at all. We really don't need to know about Q at this point to be able to answer this particular question. We're just looking at that concentration of our ions. Letter D is very similar. It's just showing that silver is the one that's more than 1 molar and magnesium is staying the same. So to be able to answer this, we need to be able to know remember, we want the cell potential to increase. So we want higher concentration at the cathode or lower at the anode. Both of these answers, C and D, are showing a higher concentration. So we need to know which one of those is the cathode. So we know which one's increasing. We want more at the cathode, more cats. Okay, so we need to decide which one's the cathode. We do that by looking at our calculation, right? Our standard reduction potentials are given here. So when we calculate it, we want cathode minus anode to give us 3.17. Well, let's just try them. We have two combinations. We've got silver minus magnesium or magnesium minus silver. So if we do silver minus magnesium, 0.8 minus negative 2.37, we get 3.17. That one matches. If we flip them and do magnesium minus silver, we get a negative value, and we do not want that. So what that tells us is the 0.8 has to be our cathode, which means silver has to be our cathode. So if we want a higher voltage, we want to increase that 3.17 to 3.25, then we need to increase the concentration at our cathode. We need silver to be greater than 1. So we can eliminate our magnesium and make D our answer. The concentration of silver is greater than 1 molar and magnesium stays the same. Now, if our options were changed up a little bit and they showed something less than 1 molar, then that would be our signal to find which one's the anode, right? The one we want to reduce the anode and increase the cathode. So if our answers were a little bit different here, it might change things up. So understanding which one needs to increase and then using our values to identify that can be really helpful. So over time, our cell potential is going to change. So once we set up a galvanic cell, even under standard conditions, as that cell operates, the concentration of your ions at the cathode, the concentration available, that 1 molar solution, is going to decrease over time as it gets used up, as those ions change into their solid form. So as that happens, they get used up and the cell potential will always decrease over time. Okay, so that is a very key takeaway from this as well. As we decrease that concentration, because the reaction is just occurring, it's naturally going to decrease. That's going to cause a reduction in our cell, or cause our cell potential to decrease. I don't want to say reduction. So that's why starting with a higher than 1 molar concentration at your cathode is helpful. You can start higher and it'll take less or take more time for that chemical to run out, and therefore your cell potential will stay higher for a longer period of time. So those are the key takeaways from this. We can change our concentration of our 2 half cells and alter the voltage. Increasing your concentration at your cathode is going to increase your voltage. And the opposite is true for the anode. Decreasing the anode increases the voltage. And in general, your cell potential is always going to decrease over time. So we'll start at its highest point right at the beginning of the reaction and then decrease. That's it for this one. Thanks, guys.